So what I'm going to be talking about are the black hole, Colin? Is that what you call the Chilcotin, the black hole? These are the best rocks. And we're going to talk about why. So let me just get organized here. So just a brief, this will be in 3 parts. So we're going to be talking about something that's very important. That's what happened at NASCO. We're going to talk about geothermal energy and then where geothermal is going in BC. So first of all, I get to be the last speaker. That's usually a horrible thing. But since you have wine afterwards, maybe most of you will stay. But I'd also like to thank the previous speakers for bringing me up to date in terms of what's happening in this area. My last footsteps here were a couple of years ago, and I'll talk about that. But no, thank you to all of them, and thank you to our Geoscience BC for inviting me to present here. And I don't think when Bruce sent me the message that, and asked me, that he actually understood the significance of this particular time slot. So just a reminder, we are part of the BC, we are part of the Ring of Fire. And there's our TREC project. What's important about it? This, in particular. So yes, the Chilcotin is a bit of a problem. I'm sorry, but it is what it is. But I think one of the most important features from a volcanological point of view is the Anaheim Belt. And the Anaheim Belt starts on, it starts over here in dike swarms that are about 8 to 12 million years old, and it ends up at the NASCO. Now, there is some contention about whether or not it's in fact a hotspot, but we're not going to go there in this talk. What I want to focus on is volcanoes in Canada. So we actually have here in BC and the Yukon an incredibly rich history of recent volcanism. And the First Nations, there's a number of First Nation stories. One of the most important and famous is actually the Siux Cone up north of Terrace. And that was probably Canada's largest natural disaster. Over 2,000 people were killed in that eruption. And again, that's another story that we don't have time for today. But there's sort of the last 5 million years of volcanism in British Columbia. There's a couple of hundred points on there. We can lump them together into 6 volcanic belts. We have lots of subduction related up here in the Wrangels, down here in the Garibaldi Belt. But we also have this big zone of crustal rifting up in the north. We have the enigmatic Wells Gray, who we also think is dealing with deep faults. And then we have the Anaheim hotspot. Oops. So these are our top picks. Why? These all have had recent earthquake activity. And by recent, I mean the last 20 years. You can see there's quite a few of them. But here it is, NASCO. So Bruce, you didn't know this, but it's 10 years ago this month that we had at one of the most important earthquake events in Canada was here in NASCO. So October 9th was when it started. I was a research scientist with the Geological Survey of Canada, and my colleague John Cassidy over in our office on Vancouver Island gave me a call, and he said, we've had some weird earthquakes. Do you know anything about the area? And of course, we looked at a map and we said, well, there's Nazca Cone there. So the last eruption of Nazca was about 7,100 years ago. It had 3 periods of eruptions, but nothing more recent than that. But again, in the work that I had actually done several decades ago, what I was looking at was, is Nazca part of a hotspot? And the results are it does fit a hotspot track. extending with Nazca being at the eastern end and the youngest. But there are some other explanations. Certainly the Itcha range, which you can see here, all the little yellow triangles are young cones. These don't fit as well into this hotspot track, but what I want you to look at is these are the volcanoes. This is the Rainbow Range, this is the Algachas, and these are all of the Itchas. These are big, huge volcanoes. Now, when the activity started, of course, a lot of us were mobilized because we didn't know what was going to happen. But we had some really neat opportunity to do things. So this is a high-resolution DEM. We can do better now with LiDAR, but you'll notice there's a lot of pimples out here. Those pimples have never been looked at. And you've had the opportunity to see what some of the bush and whatnot looks out there. It's all overgrown, it's covered with till, and these places have never actually been looked at. So I just throw that out there. So this is the area, a number of these, we had the horrible fires this summer, but fires also present an opportunity to expose some of the bedrock, so there might even be an opportunity to get out there. Now, the other thing that we found in our work was this area. And you can see the roads on here. So I was driving along on this road, and I said, there's something really weird about, as we crossed here, got out of the truck, trundled off down into the bushes, and this is a post-glacial lava flow. It's not on any maps, other than the maps that we created. It's 2 to 3 cubic kilometers of material, maybe more. But again, all of these are just to demonstrate that this is, as you've been hearing from everybody else, is a relatively unknown area that has a lot of potential for various things. And maybe, Peter, there's going to be, here's our ore deposit coming. So Nazca cone itself is a small cinder cone, last dated at about 7.1 thousand years ago. We know that when basalts erupt, they create earthquakes. So if we look back in time and we could see what was happening around Nazca, we would have seen a number of earthquakes. These are basaltic magmas. They made it to the surface. And created a small cinder cone. That cinder cone spread ash a few tens of kilometers and a lot of pyroclastics all around it. It's great building material, as you can see here, piled up, ready to be transported to the lower mainland. And a number of the new bridges that have been built in the last 10 years here in the lower mainland have used the ash from Nazca for their foundations because it's light, it won't sink, and it's very stable material. So then it happened. So say it started on October the 9th, and suddenly we had literally hundreds of earthquakes happening within a very short period of time. And volcanologists love spasmodic bursts. These wow, when we see these things, it's like, wow, what's happening? Because we know when we're seeing spasmodic bursts, we're actually seeing liquids moving. That's one of the key pieces of evidence for liquids moving. Now, don't know whether or not those might be hydrothermal fluids or whether or not they're actually magmas moving, but we know something is moving down there. So there were the other thing that caused a lot of concern is basically there were 8 magnitude 3 earthquakes that occurred on October the 10th and October the 11th. Those are pretty big for an area that doesn't experience earthquakes. So it's the GSC, the group in Ottawa that is responsible for the network, got out there, and you can see it was snowing, it was cold, it was minus 15. The equipment here, the seismometers, have to be set in the ground in cement. We had little tents and clever ways to get that cement to actually set up. And we were able to do that. 4 stations were installed. We also, this is Glenn Williams-Jones of Simon Fraser and one of his students. One of the things along with earthquakes that you see is actually carbon dioxide. So Glenn had the instrumentation and he went out with a student and we did some transects. And of course we also looked at the geology. And that's why, or how I identified that post-glacial large lava flow. So with all of that work, what we were able to identify is that, in fact, magma was moving, and it was moving at depths of about 20 to 30 kilometers. These little circles, these are the new seismic stations that were installed. This, you can see there's actually a problem here in terms of data interpretation. These aren't in nice little lines, they're more like a lump, but that's the earthquake swarm. Here is some of the velocity structure that was used to put together. So those 4 stations, plus additional stations, were used to identify where these earthquakes were occurring deep in the crust. This is what the epicenter looked like. Not very exciting. And there was certainly nothing on the ground. But with the seismic stations, we were able to track the magma. So what you see in these diagrams on the right-hand side is these are times. So the red are the most recent. These were into November, beginning of November, and the first dates were in purple. So you can see that it actually moved over the days. Not in any particularly coordinated way, but it was moving. So here's an east-west or west-to-east cross-section, and you can see it sort of started over here and actually moved laterally at a rate of about 0.5 kilometer a day, with the last gasp that we saw here in more of the central portions. A bunch of papers came out of it. This is one of them, because these are actually very rare events. And to be able to capture it, to be able to collect the data that we were able to be able to determine the location and the depth and the type of earthquakes is actually quite rare. So it generated a lot of interest. Now, I actually started my career way back when in Mount Meager. So Mount Meager is down here. Those of you might know it. It's noted as a beautiful, well, it's a beautiful mountain area, but it also has a hot spring. So back in the early 80s, there was a program with the Geological Survey of Canada. It was funded under the, well, there was an energy component. And it started actually in the mid-70s when the price of gasoline was getting very high, and people thought that we were going to, well, not so much run out of gasoline, but it was going to be too costly, and so there was a big effort to look at geothermal energy. And that started a lot of work from a number of different organizations, and that has continued to the present day with work being funded by Geoscience BC. So this is sort of the latest heat flow map. And I showed you the picture of all the volcanoes. So, you know, many of these areas are areas that we know are volcanic, but what you're seeing over here is the Western Canada Sedimentary Basin, which has hot fluids which are up to 120 degrees C and are tapped by the oil wells there. So it's not just high temperatures that are associated with volcanic deposits. It's also these deep sedimentary basins. And you'll see over here in the Okanagan, same thing, is we have a deep sedimentary basin, not obviously as deep as the Western Canada, but that is actually creating and trapping hot fluids and has the potential for geothermal energy. So we picked up 18 specific localities, which are shown here in stars. And these are areas that we thought were particularly important or had the potential to be good geothermal, have potential for geothermal. And you'll notice Nazca Cone. And of course, why Nazca Cone? Because we have this amazing history of volcanism in this area. So what is geothermal energy? Now, when I'm talking about geothermal energy, I'm not talking about ground-based. Many new buildings have essentially a heat pump type of system. You drill shallow holes, you pump heat down in the summertime, and you retrieve that in the winter. What I'm talking about in terms of geothermal is temperatures, groundwater temperatures that are above ambient and can be used either at higher temperatures for electrical generation or at lower temperatures for direct use. And typically, high temperature, to produce electricity, you want to have temperatures above 120. But what do you need? So, Craig, you started off with monkeys. Here's more monkeys. So what is it? And at high enough temperatures, it can be efficiently used to create electricity. So this is not new technology. This is actually in Italy. Those of you who happen to like to go to Tuscany and drink the wines, you're actually in an incredibly large, productive geothermal energy area. Larderello is the famous locality, and this is the first plant. It ran a light bulb, and it was built in 1904. But what I think is really important for British Columbia is not necessarily the electrical generation, but in fact that direct use. So just a little schematic. I mean, basically we need to add groundwater, we need to have warm, that groundwater needs to percolate through fractures. It is heated up either by volcanoes or simply by the temperature gradient in the earth, and then we can tap it. This is just a very schematic of a plant. You know, hot water comes up, we can run it through a turbine if it's hot enough, cool it down, and then we pump it back in. Typically, most high temperature geothermal facilities now have a direct use. So they use that hot water, instead of pumping it back down into the ground, they use it for a number of different purposes. And it's energy. So heat is energy. So anything that you can think of that requires energy, I mean, you can use hot water. And typically, we're only thinking about things like spas. This is Fairmont up in the Rockies, but it has been used in a number of places for space heating, things like greenhouses and kiln drying of wood. So anything that you can do with heat, you can do with geothermal. The economics, that might be a little bit of a challenge, but we'll get to that. So so back to Nazca. So we have this cinder cone. I've already showed you that it's part of the Anaheim belt, or we certainly have this belt of volcanoes that go across the southern area of the trek. But it's relatively young. We had our seismic event in 2007. But around Nazca Cone, there are these two bogs, the South Bog. And so we're now looking, this is taken from an aircraft, and it's basically over the cone, and it's looking to the northwest. So these bogs, now segue even further. I had left the GSE in 2008, and I joined a company called, well, that time it was called Magma Power. Now it's known as Altera. And we were looking in BC to identify and hopefully develop some geothermal potential areas here. So these bogs, so young volcanism, the bogs around there that were full of calcareous material, they had CO2 degassing, were certainly of interest. And in fact, here's Ron sampling. And some of his early work were based on the work that we were trying to do in the field. Get out there and get some rapid analysis that, yes, we would later follow up with in the lab, but were quick and easy and helped us target and pinpoint where we were going to go. So that was kind of happening in 2008 to 2012. And that's a period of time. There was not just Terra working in British Columbia looking at geothermal. We had some of the biggies here. We had Ormat was here. We had Enel, an Italian company. They were all looking in British Columbia. But unfortunately, 2008 was a bad year for not just geothermal, but also in the mineral industry and many industries. That was when we had the stock market crash and various things started to happen. So a lot of these companies who were active in that 2009, 10, 11, 12 years sort of gradually went away. But the geothermal energy is still there. And in fact, in the world today, we're looking for green alternatives, sustainable. So more work needs to be done. And in fact, I worked with the Nazca First Nations, and we looked at what the potential was for the Nazca area. That was back in May of 2015. And what we noted there is there's some incredible geoscience data sets that have not been completely plumbed, that are sitting there. So these were work that was done. So this is by Ray and I were just talking about this earlier, and Wayne. So they went into the bogs that you saw the picture of. They did additional work. We also did some helium analysis, and there's a slight indication that we're actually getting mantle helium, so a volcanic source for these the material that's being deposited here. Then Geoscience BC has gone on to promote a couple of other or fund several other reports. One is for the electrical generation of British Columbia, and the other is on direct use. So those are all available and downloadable from the web, and I think are a great starting point, along with these data sets, which have been generated by Trek and by Quest and a number of these projects, which have been funded by provincial and federal governments over the last more than a decade. There is, and I was happy to see Andy Calvert here, because there's an incredible seismic data set that has not been looked at from the perspective of, at least not to my knowledge, but has not been looked at from the perspective of geothermal energy. There's an MT survey, again, that hasn't been looked at. And these were all gathered in the sort of 2008, 2010, 11 time period. So those are all waiting for someone to have a look at and really decide, because all of the other indicators are there. Young volcanism, Craig showed us all of his faults, the structures. We've got sort of all the underpinnings of a resource. What we don't have, other than at Nazca, is surface manifestations. We don't have hot springs, we don't have fumaroles, some of the things that would make it even more enticing to go in here. So just want to remind you, there is more volcanism out there that has not been tabulated. One of the things about basaltic volcanism, it tends to come to the surface very rapidly. And there isn't a lot of time to develop a robust geothermal system or hydrological system around the rising magma. But if you have enough of it and it penetrates the crust often enough, then that's good evidence that there may be something there. We've already talked about the Anaheim Belt, and just these are big volcanoes. These are the biggest volcanoes that we have in British Columbia. So even though we may not see a power plant in the lava flow anytime soon, I think that there is the potential, and I think in the interior of British Columbia is certainly one place that we should be looking at. One thing I will say, though, is that I believe that it's not going to be built by the private sector, that it will need government support to do the additional geoscience work that needs to be done to identify that there is a resource there. So thank you very much. I'm glad to be the last speaker, and if you get questions, thank you.
Thank you very much, Cathie. So let's just move right into discussion and questions, and if anybody has any comments. We really would appreciate it if you could use the microphone so that it can be captured by those people who are attending online. All right, maybe I'll start off one with, oh, there we go. Okay, go ahead.
Peter, it's a very interesting introduction to your paper about epithermal systems in general, and the Rio Day site and the massive size of some of the systems that you're targeting right now at Mineral Hill, I think it is?
Fenn.
Fenn, is it Fenn? So your view is would it fit in between a low sulfidation or high sulfidation system, or is it a completely separate system at all? You'd ignore the old system?
No, I wouldn't ignore the old system because the alteration fits. So it's a high sulfidation. But really what I was getting at is that just calling it high sulfidation doesn't tell much of a story. I don't know if you've ever gone in a boardroom and said, well, I've got this high sulfidation epithermal deposit. It doesn't get you any money. But if you can say, oh, I've got a Blackwater lookalike, that gets you some money. But that's, okay, I'm being a little bit cute there. But yeah, no, I just think that there is enough of these deposits that have these similarities that we could work up, or the industry could work up a really good model for these if someone wanted to put the effort in.
Yeah, I thought the description of Blackwater with, especially with this zinc signature, the sphalerite, which is similar to yours.
Yes.
Except you had more lead in yours. Is that correct?
Actually, I don't know what the lead is in Joel. Where are you? Sorry? Fairly low.
It's very low. So,
Yeah.
so it sounds like it's more similar to Blackwater in that sense too. But there's a lot of other deposits that are fairly sizable, big tonnage, diatreme related, which you mentioned in your, I think in one of your models at least. I'm including Montana tunnels and Sunshine, Kidston, which are all diatremes, are all gold, breccia related, but it's diatreme in that sense. And a lot of them have zinc. You know, it's trace amounts. You're talking
Okay,
0.2%. So do you see that kind of similarity with the Fenton and the Blackwater?
I'm not sure exactly how to answer that. I guess from what you said, I do. I mean, I went looking when I first started working on Fenton. Well, actually, it was actually back with Esso. I knew that there was this rhyolite dome out there that had a bunch of zinc in it, but I just didn't know how it fit into the scheme of things, right? So it only came after actually. I started looking at San Cristobal in Bolivia, and I thought, oh, well, that's kind of interesting. Maybe it's one of those things, and it evolved from there. And so I'm not sure about the diatreme breccias. I think they might be there. You know, maybe they should be on their own setup. But I would say that any place where you had a rhyolite flow dome, or if you've got one there, or you had one there but it's been eroded, then maybe you should be looking at this type of model.
Have you looked at Round Mountain?
Yeah, that actually would probably fit quite well. Yeah, I did. To be honest, I did focus on the ones that were more silver enriched than gold enriched, and that sometimes that's just a factor of metal pricing more so than actual crustal abundance or enrichment.
All right, thanks. Questions popped up here that we can go straight to for Ron. Can you take the microphone, please? What is the cost to an explorer to get set up for a rapid hydrogeochemistry program? So maybe you can address both the capital costs and operational costs.
Well, it depends what you want to look at. If you want to look at a small area, obviously it's not going to cost as much. Operational cost.
Setup, like what's the capital cost to get into this?
Depends what you want to do. So some of the equipment ranges from a few $100s to tens of thousands of dollars, and that's just for the equipment itself, and then you have the additional cost of the reagents, and then there's a learning curve. So you're looking at probably a few tens of thousands to have a really good program in place. For operation, depends who you want to operate it. If you're hiring people, you can probably train students to do that. If you do it yourself, so it'll obviously be cheaper, but then it's the time you're putting into it. So for the study we just did over there, you know, we're looking at 6-digit figure, but again, depends on what you want to do. You can probably set up for a few $1,000s and start sampling and see what you learn. Or you can do a more methodical program and for low 6 digits, but you'll be getting hundreds of samples from that. So it's really, again, going back, it really depends what you want to do.
Peter's got a question.
So you can keep the microphone.
Oh, okay.
So could you analyze Colin's tree sweat?
I was just about to say to Colin that the copper concentration there looked that I could start doing those. Because until now, when we talked to Colin and Dave, a lot of the stuff you looked at was really the PPT stuff, but I just saw the copper there, and we can do that. So, yeah.
So copper, sorry, Colin, your copper numbers in the exudates were in the hundreds of ppb?
No, they
No.
were lower than that.
Tens of ppb?
Sorry. I think they were in the 10 to 20 ppb range. I'd just have to check back.
Yeah,
I think it's lowest were single-digit ppbs, which I can do.
yeah. But that's doable by the photometer
Oh, yeah.
method? Yeah.
We're getting good, reliable data for single-digit ppbs for copper, both on the dissolved and the totals.
All right.
Yeah.
But you did have very high percentage issues with the copper analyses, right? The precision wasn't so great.
In what way do you
Well, I
mean?
think, didn't you have like 10% errors?
No, this is just when you repeat the samples, you get
Oh, the
1
reproducibility.
ppb or 2 ppb. So what we did, we average it. And when you look at the lab is more precise, more decimal points.
Yeah.
So it was getting 1.2, right?
Right.
But it was not an issue. What it was is just making sure that you get a good solid number. But the results, you know, if you get, the problem with the photometer is really decimal points, unlike the lab, right? So you got to average your results.
Okay.
So what you're saying is you could do one of your water surveys in the desert.
Yes. Anywhere you can sample water, you can take these devices and do sampling.
Other questions? Actually, so while you've got the mic, so the other one, you said sulfate always works. And
It's
then-
an indicator for almost everything. Almost
so-
everything.
So could you just work on sulfate and then follow up afterwards, or?
Well, that actually is an option, because if you don't want to do a full suite and you want to do it faster and cheaper, you choose 1 or 2 indicators, you go out there and look at them, and then you do follow-ups. So if you do 100 samples and you only get 10 of them, then instead of replicating everything, you just follow up those 10 and then you do full suites. And that's the part about the points I have about flexibility and customizability. Really, the sky is the limit of what you want to do with this device and the testing. Unlike a suite where you're locked into a suite, you can actually pick and choose what you want to do that. And if it's if it's an easy area to go back to, then you can go back and do these things over and over again, and not only get better reliability, but also really get a good data set that you can work with later on. And it's just a tool, right? It's not the means all, but it's a good first step, but it's also a good second step and a third step, right?
How does conductivity and pH relate to your sample?
Most of the samples are natural water, so most of the pH is about 7 plus minus. So it really does not a lot of changes in that. When you start looking at low pH, like 2 and 3, you got to add a buffer to it to have a look at it. But there's really not a lot of effect from these two that you're talking about. A lot of natural water is very stable, so you get good results with that. Is that what you meant?
I was wondering if you had metalliferous solutions, whether they would commonly have a more acidic pH, and also you can measure conductivity directly. And I wondered if there's any relationship with anomalous metals, with something that you might field measure very simply.
Well, conductivity and pH we do with a meter, not with the photometer.
Exactly.
Yeah, it's been very reliable in the field. But there was a relation with conductivity and pH. So if you get a mineral spring, pH goes down, conductivity go up, and you get the associated minerals with that. And of course, the more acidic it is, the more stable and higher results are the mineralization, especially from springs. So really what you want to do is you want to look at your natural water and identify your spring water, and that's really what you want to find and then send to the lab if there's good results in it. But the whole purpose is to identify the area and then follow up and find the springs, because that's the groundwater. That's really your ground signature, and that's where your mineralization is going to be.
Question for
Ron-
Sorry. Question for Cathie, please. In the NASCO area, if you wanted to find a drill target for geothermal energy, how big an area do you think you'd have to search in? I mean, how big an area do you need to survey?
That's a very good question. So if you had asked me that when I'm funded by a big company that has lots of money, a really big area. I think now is what is important is the likelihood of getting hot enough water for electrical generation is low, but you've got direct use. So you drill where you have a potential for direct use, the community. And your first hole is a 300-meter hole, and it's basically a gradient hole. That's your first target, is as close as you can reasonably get. You would choose whatever structures, you know, if you have a fault, like for instance on the along the village of Nazco, there's a big fault there that goes along the river. So you target the fault. You won't need to get down 300 meters simply because you've got to be below sort of the natural groundwater. You want to really see what the gradient is, and you use that to go forward.
Would you use EM, like MT, to map out a target?
Yes, so with the data sets that are there, if you wanted to do a whole regional study, then, so my first answer was for the cheap and dirty. Let's see what's there. If you want to have a much more robust, then absolutely, you've got seismic, you've got EM. I mean, even things like the chemistry and whatnot are telling you something, the physiography are telling you about the underlying material. So you use all of those together to develop an exploration program. And the road network is important.
Thank you.
Well, you've got the mic, Cathie. So is that whole Anaheim belt burping and farting CO2 and methane? Like if we had sensors out there all the time measuring 24/7.
Certainly NASCO is. There's fairly significant amounts of CO2 that are being released. No, as far as we know, like the Itches, the Algaches, there aren't any hot springs. So what you need, there may be some soil degassing, but we don't see any evidence of it. So no, NASCO is the bad actor, but certainly volcanoes, active volcanoes do put out thousands of tons, millions of tons of CO2.
Right. But you know, the NASCO example you showed with the seismicity, that was down in the mid-crust. And so do these things sort of stage down there and then just wait for the opportunity and come all the way through? Or do they have a thermal footprint associated with them?
So for rhyolitic eruptions, yes, what we see is that the magma comes from the lower crust. It will go to about 10 to 15 kilometers in depth. It then creates a magma chamber, and that's where you get your nice mineralization starting to form as it crystallizes. And then as it crystallizes, it increases in its volatile content, decreases in density, and then is able to erupt to the surface, or not, right? So in the case of basaltic volcanism, the reason that this was such an interesting event, because it's a fairly rare event to capture, because what we think happens in basaltic volcanism is it starts in the lower crust and will literally come to the surface within days to weeks, with very little other manifestations other than the seismicity. So quick, fast, that's why we don't see geothermal systems associated with it. In the case of rhyolites, you do.
Right. Are there any paleo hot spring evidence?
Yes, there's a lot. Well, your mineral deposits in many cases. Those are the paleo hot springs, you know, depending on the type, obviously. But yes, and in fact, up in Ziza in northern British Columbia, there are significant evidence of hot springs, including geyserites. So geyserites will only form where you have geysering activity, and because the churning of the water and the deposition forms a very specific form of quartz, and you get geyserites. So at Ziza, yes, there were geysers there probably 500 years ago. In the Elgaches, we do see evidence of certainly alteration and hydrothermal, but currently no hot springs.
Any questions from the floor, comments? Wait,
The Gaucho's range, they're paraluminous. Does that tell you everything about whether it's a hot spot or not?
Yeah, so the thing about the hotspot is it does fit what we call an Euler pole. So you can track in terms of the age and what we know about the movement of the North American plate. It does follow. But there have been people who have pointed out, Derek Thorkelson being one of them, about plate edges. And certainly the itches is a very odd, the way it extends much further down to the south. But yes, and the chemistry tells us something. So that these are paraluminous, they are odd. You have all sorts of really incredible, from a volcanologist's point of view, things on keramites and very rare kinds of felsic volcanism, which is related to hotspots.
Ron?
Ron, I was very curious to know about the ability of normalizing data in hydrogeochem environments using silica. Is there conditions where you would use it definitely or all the time, or do you check it some other way as well before normalizing your other data?
Well, I would use it if weathering is inconsistent, not necessarily geochemically. So some days you'd go out there and it'll just be pouring rain, and you tell the difference from your data from the previous day that your copper just dropped, right? So by normalizing with the silica, you'd get a better consistent results. And we've done that with the study, but there was really not a lot of changes that we needed to show, right? So October was terrible. I would sample one point and it'd be nice and dry, and then you'd go to another area and it was just pouring rain, and you can tell how with the meter, how the changes were occurring as you're there. So so what you want to do is you want to make sure that you have a baseline of something that's very stable, and then you can normalize it later on. So you don't get these anomalies that you think there are good anomalies, but in fact it's just weathering effect. So that's really what it's all about.
Last chance for a question? I have one. So Colin, you showed data that was ash and dry.
Yes.
Why are there different approaches?
By ashing, you would concentrate twigs chemistry about 50-fold, and needles about 20-fold. With the TREC survey, an awful lot of the data from the analysis of the twigs came out below detection level of 0.2 ppb gold, for example. I don't think there was a single sample that came out higher. So that would be the advantage. People are suspect of ashing because, and it does have its problems in that you will volatilize all of the mercury. You may volatilize some of the arsenic, antimony, but with those elements, it'll be a pretty consistent ratio as long as you have constant ashing temperature. But to get your highest anomaly, contrast, and therefore best precision, ashing. But the analytical technology is just on the cusp, and it's a bit of a judgment call as to what you ask the lab to do.
Right. Okay. Thank you.
After all these forest fires, we can go out and collect the ash and analyze it.
I had nothing to do with the fires, honestly.
Well, we're about to wrap up here, and one of the things I recognized as the day went on that we were remiss in not appreciating where we started a lot of this Trek project. And so I really wanted to recognize Andy Calvert and the work that he did with the Nechako project previous to Trek. Particularly, he was looking at the seismic and the three-dimensional components of the Nechako Basin, which really provided a great platform for understanding a lot of what we moved on to into Trek space. So I don't know if Andy's still here. But it was earlier. Anyway, I wanted to recognize that. I also wanted to recognize Peter Kowalczyk. He designed the geophysical surveys that happened in Trek and was part of the early interpretations of the magnetic data sets, which I think is critical. And I think also the most critical thing that I can see is Dirk Tubman-Cluett, who filtered through hundreds of assessment reports before recognizing that Blackwater-Davison was a place worth investigating and following up. And of course, we all know where it went from there, but that really attracted attention to a region that really hadn't had very much attention, and so I think I want to recognize his contribution for that as well. Join me in thanking those individuals as well as everybody on stage. Thank you.